Okay, again, hello everyone. Today we're gonna continue on the properties of second order tensors and also equations of motion in turbulent flow. So we were reviewing fundamentals of fluid mechanics, and there we just said that there is a property called contraction in second order tensors, and this contraction refers to a special condition when we have two indices, the same indices, like what we have shown in here. So we have BII, for example. So B is a second order tensor, and these indices are the same. So the BII is the trace of B, and now we have double tilde sign under B, representing that the B is a tensor, is not a vector anymore. And you remember that it is B11 plus B22 plus BT3. So why is this important to us? Because the value of trace can be used to decompose this second order tensor. Okay? And we will see how. Actually, any second order tensor in mathematics can be decomposed into an isotropic part and deviatory part. And we can further decompose this deviatory part, whatever it is, it doesn't matter, it's just a second order tensor, okay? We will decompose it into a symmetric part and anti-symmetric part. And trace is needed to do that. For example, when you decompose the deviatory part of velocity gradient tensor, its symmetric part will become what we call a strain rate, and its anti-symmetric part will become rotation. And we will see it in more details, don't worry. These are all mathematics, but we have to keep relating everything to the physics. And let's say we have one of these second order tensors, the isotropic part, for example, the isotropic part of velocity gradient tensor. In general, when we say isotropic, we mean there is no change with respect to direction. So if you have isotropic velocity vector, it means that its value does not change when you rotate it, and it keeps its value after rotation. So isotropicity means this. Isotropic tensor has the same components in every coordinate system, as we said. And the coordinate systems can be defined in any manner. The thing is, what if I write a tensor with respect to another coordinate system? In order to do that, I need to know how much the original coordinate system gets rotated. If I know that rotation, I can do rotational transformation. So in 3 dimension, you have these three matrices for the rotational transformation. For a vector, when you do this, you will get these three different values for the vector components. But one thing will not look different when you rotate it. Rotate that, let's say, tensor, and that is the isotropic part of that tensor. The isotropic component has the same value in any coordinate system. Is it clear? Do you have any question on this? So,
No.
yeah, I will explain in more details when we proceed. The isotropic second order tensors are scalar multiples of Kronecker delta. So these are all properties, okay? What does this mean? For example, if I have Bij is a tensor, and if its isotropic part, I name it, I call it as Bij superscript I. It stands for isotropicity. Uh, it means that the isotropic part of Bij is 1/3 of BLL delta Ij. So BLL delta Ij, this chronicle delta, remember, this was there to just change the indices of BLL. So you have two L's in here, so one is it will be changed to uh, I, and the second one will be changed to J. So you will end up with Bij isotropic. In order to match the indices, actually, I have this Ij in the left hand side, so I have to have this delta Ij in the right hand side to match this. The BLL is, this was a trace, so actually it denotes the summation. BLL is actually B11 plus B22 plus B33. And unlike the isotropic part, the other part, the deviatory part, um, it's a fancy name, so it is given for something that means it is changing with coordinates. Okay, the isotropic part is not changing with the coordinate, but deviatory part is changing with the coordinate. So this deviatoric tensor, we call it Bij prime. So Bij, um, the deviatoric part is with prime sign, the isotropic part is with I sign. And deviatoric tensor, Bij prime, has zero trace by definition. So we actually define that the trace of the deviatoric part is zero. You have to remember this. So how to calculate it? It's nothing but so your Bij, actually your second order tensor, is made up of Bij prime and this part, which is your Bij uh, isotropic part of the Bij, the 1/3 of the trace. So that's why the trace is important to you. You have the trace in this definition. You have the original matrix Bij, and you add up the diagonals in BLL, and you take 1/3 of that thing, and then you subtract it from each component of the original matrix, and you obtain a new matrix which is called deviatoric tensor matrix. And if you add up the diagonals of this matrix, by definition, you should get 0. So we have all of these properties right now, so you should keep in mind all of these properties. Next step is to further decompose the deviatoric part. Okay, we said deviatoric part has symmetric and anti-symmetric. So we have to decompose this deviatoric part. As you see in here, you can name it as symmetric part, Sij, and anti-symmetric part, Rij. So what is Sij? You can define it as half of uh, summation of Bij prime and Bji prime. And the Rij is half of the Bij prime minus Bji prime. So using these definitions, one can write the original tensor Bij, so this is the original thing, as uh, actually the isotropic second order tensor and the symmetric part and the anti-symmetric part, as you can see in here. Now, let's apply these mathematics to physics. All these properties of second order tensors that we've seen so far, like decomposition, isotropic, symmetric, and anti-symmetric part, what do we get when we apply all of these into velocity gradient tensor, for example? So this means that your velocity gradient tensor dui dxj can be decomposed into three parts. And when we do that, we will get this. We'll get this. And the isotropic part of dui dxj does not exist. So the isotropic part is equal to 0. Let's look at the matrix notation. So these three decomposed values of velocity gradient tensor all have some physical meanings. And as you can see in here, first of all, the trace is 0, okay? And it represents the continuity equation, as you see in here. When the trace is 0, it means the continuity equation in incompressible flow. It is seen in isotropic components. That's why the isotropic components is equal to 0 for incompressible flows. The symmetric component is actually what we call the strain rate. Okay, this is the symmetric component, strain rate, and shows the deformation of fluid particle. It could be either shear strain or normal strain that deforms your fluid. And the third part, which is your anti-symmetric part, is actually the rotation or rate of the rotation of the fluid particles. These are some fundamental things we define in the first weeks of fluid mechanics. For example, a strain. What do we mean by a strain? Usually we draw like this, a two-dimensional square representing a cube, and it gets strained where we say that at a later time, like t plus dt time, it cannot hold onto its shape, and its shape will change and it will look more like parallelogram. So we try to relate these deformations to the angles. You remember these deformations to the angles that are made and everything, and this information, this deformation or shape change is related to how much you strain. Like in solid mechanics, it is related to displacement and deformation of an object. The rotation is something different. As you see, if you have a fluid particle like cube, and at a later time, due to velocity gradients that are present in the flow or forcing on the fluid particle, the particle is rotated. It's just rotated. So rotation is kind of motion, but a strain represents a kind of deformation. Please keep it in mind. That's why when we talk about turbulent flows, which I showed you specific canonical examples like these wakes and jets and etc., I draw examples of velocity profiles. You remember I put it once more in here. It belongs to the previous lecture. These are the velocity profiles. If you look at those profiles, they are not uniform profiles, right? The wake is something like this, the jet is like this is the shear mixing layer, this is the boundary layer, this is a plume. So they are changing, and it means there is velocity gradient in the flow. And when there is velocity gradient, then you would expect that this dui dxj will will not be zero anymore because you have velocity gradient. If this velocity gradient generates some eddies or structures, that eddies and the structures generation and their also their geometries have to be related to the velocity gradient and therefore to the strain and rotation in the flow field. Uh, these are kind of uh, just a second. These are a kind of starting points how actually we link these fundamental second order tensor properties to the generation of turbulence. And later we will write more equations when we come to turbulence modeling part. And you will see that many of the turbulence models, even very simple algebraic models that are known as zero equation models as well, they use a strain rate, and some of them they use rotation rate to calculate the turbulence stress. What is the turbulence stress? You remember it was ui prime uj prime bar. So this is called the turbulence stress. We will see that this turbulence stress is just a mathematical artifact when you do a statistical averaging on normal Navier-Stokes equations, it shows up itself. We don't know what it is, physics. Still, we don't know, and we really we have to solve the equation. So we have to develop a model for this thing in here, and we say that okay, look, this looks like an stress and it does have a unit of stress as well because unit of it is meters square per second square, so it does have a unit of stress. We also know that um, solid people calculate the stress from strain, so we say that why don't we do the same thing? We have the stress and let's use the strain or a strain rate in reality. In fluid mechanics, instead of strain itself, we use the strain rate of change of strain to calculate this stress. This is how it all started, the turbulence modeling, and the idea of trying to calculate the turbulent stress, this tensor using this strain rate tensor is called what we know as Boussinesq assumption. Do we have any questions so far?
No hocam.
Okay. I hope everything is clear for you. If I just speak very fast, tell me. If something that you did not understand, just tell me.
Okey hocam.
So we were talking about these second order tensors. We described how we decompose second order tensor, and just to summarize, we are interested in second order tensor because the second it is the stress and the strain are second order tensors, and we will see that having two different kinds of stress in fluid. One is related to viscosity, viscous stress, and also we have turbulent stress. We have to understand how we should deal with second order tensors. So we will continue with some tensor mathematics and then the actual flow equations. So there are few other concepts. The first thing we saw, was related to decomposing of second order tensor. We saw that we are able to mathematically decompose it into isotropic and symmetric, anti-symmetric, and when we decompose the velocity gradient, what you get was uh, strain rate and rate of rotation, and this part is the isotropic part, which is zero for incompressible flow. And basically, velocity gradient dui dxj is generally um, it's very heavily used in modeling efforts. So that's why we are always giving the example of velocity gradient tensor. In addition to being able to decompose a second order tensor into its components, there are other properties. One of these properties is the principal axis. So principal axis for any second order tensor, which we generally represent by a 3 by 3 matrix, we can find a special set of orthogonal axes which could be different than the original axis in which you measure your velocity, for example, u, v, and w. This orthogonal axis can be very special. What is so special with that orthogonal axis? We will see in a moment. All of these things, stress calculation, stress and strain definition, principal axis and invariance, and so on and so forth, are valid for solid mechanics as well, and we are using it in fluid mechanics. So for symmetric second order tensor, like a stress, like a strain, like anything, if S is a real symmetric matrix, so S is a real and symmetric matrix. Symmetric means that S12 is equal to S21, S13 is equal to S31, and S23 is equal to S32. So if this is a 3 by 3 symmetric matrix, there exists some matrix like A. So we have A matrix such that A transpose S A, I mean multiply A transpose multiplied by S multiplied by A gives you matrix lambda, and you know from linear algebra that these diagonal components, the lambda is a diagonal matrix, and these diagonal components, you know them as eigenvalues. So lambda 1, lambda 2, lambda 3 are eigenvalues of matrix S. The question is, how do we find this matrix A in here? So there should be some matrix A that you transpose it, multiply it by S, and then multiply it by A again to get the diagonal matrix of lambda, the eigenvalues. Can this A matrix be anything? So the answer is no. A matrix is also a very, very special matrix. Actually, the columns of this A matrix are eigenvector components. So you already know these, but in any case, I have to repeat all of this. These eigenvectors are actually like your unit vectors. So the first column is related to the first eigenvector, and so on. So E1 is like, let's say, orthogonal system of x, y, z. E1 is like I, and E2 is like your j, and E3 is like your k. You know, in Cartesian coordinate system, if you're working with x, y, z, in order to represent any vector, we define unit vectors I, j, k, along our x, y, and z, our coordinate axes, and those are our orthonormal unit vector system. So we use those unit vectors to write any components of any vector. Any components of any vector is written like uh, 3i, 2j, plus k. So it's like this. E1, E2, and E3 are the same. So they are orthonormal. Orthonormal means three-dimensionally orthogonal unit vectors. And they will provide, as it says, they will provide orthonormal basis for a special coordinate system called principal axis of S. So this is the definition of the principal axis. Remember that. Uh, mm, okay, these S matrix is a symmetric matrix, and the A matrix is the eigenvector. Actually, eigenvector matrix, eigenvector components. Therefore, finding these eigenvectors is very, very critical, and they are actual orthonormal basis for your new axis system. This new axis system is special. You could have your original second order tensor, whatever it is, maybe it is your velocity gradient, maybe it is a stress tensor and something else. It has, for example, velocity gradient, it has 9 components. It's a 3 by 3. So it has 9 components. Let's say you did some measurement and you measured all these components. Okay. Say you're using whatever PIV or hot wire you have measured the flow at some point or some field, and you have all of these. You measured all these components and you want to take gradients with respect to x1, x2, and x3. So these x1, x2, and x3 are, let's say, orthonormal basis that you have. x1, x2, x3 orthonormal basis. So the velocity gradient is very well defined using this x1, x2, and x3 coordinate system. If you take this tensor that you have, this dui dxj, and rotate it, it may be hard to actually visualize how to rotate a tensor, but mathematically it is exactly the same as when you rotate a vector. Okay, rotating a vector means I can write a vector with respect to coordinate system 1. So 1, for example, this is the first coordinate system xy, and then I want to write its components with respect to coordinate system 2, which is the prime coordinate system, x for x prime, y prime. Of course, it will have different components if I somehow know how much. For example, if this is the vector that I have, so in this coordinate system, the old coordinate system, it has these two components. In this coordinate system, it has these two components. So if I somehow know how much the new coordinate system is rotated with respect to old coordinate system, so I know this theta angle, then I can relate these two. Um, I can relate the components of vector 2, vector in new coordinate system to the old one. Remember that we categorize our variables as scalars. You remember these scalars, vectors, and tensors, right? At a specific point in space, there should be either 1 or 3 or 9 different values to describe them. right? A scalar with one value, vector with three value, and tensor with nine value. The question is, how do we apply this rotation for second order tensor? This is what we call tensor rotation. Basically, you will define a rotation matrix, which I showed you in some previous pages. Is in here. These are the rotation matrices. So basically, you will define a rotation matrix which has components, and components are functions of cosines and sines. You're seeing it here, of theta. And if you multiply the rotation matrix with your tensor matrix, you will obtain a new matrix. That's how you actually rotate a tensor as well. So going back to principal axis, this theta that I'm talking about, theta angle, could be any number, but somehow you know it and you rotated your tensor, and in the new rotated coordinate system, if the unit vectors are the eigenvectors, so unit vectors should be eigenvectors, then this new coordinate system is your principal coordinate system. It's called principal coordinate system. And somehow magically, when you find the components of rotated tensor, it's a diagonal matrix. So it will be like matrix lambda. That has physical importance, regardless of being fluid or solid. These off-diagonal components are called shear components. Okay, and in this matrix, all shear components are zero. If the tensor is a stress tensor, for example, they are called shear stress. And if the tensor is a strain, they are called shear strain. But these off-diagonal values will not be present if you write the tensor in principal axis. You remember it from your solid mechanics back in your undergrads. You were rotating forces or stresses onto their principal axis. So you might be aware of these things. So in this new coordinate system, there is no shear. It means that there is no shear. There are only diagonal components, lambda 1, lambda 2, and lambda 3. And these are called normal stresses, which are either compression or tension. And how much is this compression or tension values? Those values are your eigenvalues along each eigenvector direction. That's why we need to know if there is a fluid flow, whether a complex flow or a very simple flow, in order to start doing turbulence modeling or simulation. The effect of turbulence is when you do averaging. It creates extra terms with a unit of stress, as I said. This means that the effect of turbulence literally, locally, it forces the flow to have shear, or at principal coordinate system, it forces the flow to get compressed or stretched. And if you understand this physical mechanism, then you can model that. That's why we are trying to understand all of these basics. So let me have a small break, and we're gonna continue in 5 minutes. Okay, can everybody hear me?
Yes, I can hear.
So, before we continue, uh, I wanted to ask about the seminar topics that you choose. I already know the topics belonging to Osman Veysel Özdemir, and also the first, let's say, paper that I have assigned. Osman is responsible to give the presentation of that paper as well. About the seminars, uh, what did you choose and what will you choose? Please tell me at the end of this class. You have to choose it as soon as possible.
Okey hocam.
Thank you. Okay, so you saw that having shear depends only on your coordinate system. In other words, it looks like that you have shear in some coordinate system, but in reality, if you look at your tensor at its principal axis, everything happens due to normal stresses. So it depends on the perspective that you are looking at. A scalar is direction independent. So uh, after any rotation, it does not change. What about vectors? We know that vector components will change after rotation. But is there any property of the vector that will remain the same after rotation? Its magnitude, yeah, actually remains the same. There are some parameters which we call them as invariants. Invariant means they do not change when you change your coordinate system. Scalars do not get affected by rotation by themselves. But for vectors, one of the invariants of the vector is its magnitude. And there is this question, is there any invariant for the tensors? So um, these invariants, as you see in this slide, are values that stay constant in every coordinate system. And we said the norm of a vector, which is its magnitude, is an invariant, the norm of the vector. And for the second order tensor, like Bij, a general Bij tensor, which is like this, B1, 1, B1, 2, B1, 3, we will define actually three invariants. So first invariant, second invariant, and third invariant. What is the first invariant? First invariant is nothing but the trace. So the trace will remain the same. It doesn't actually depend on the rotation. If you just express your vector, your tensor in some coordinate system and calculate its trace, it will be the same as any other coordinate system. The second invariant is defined by 1 over 2 factorial times bjj minus bji bij. So probably you should be able to calculate this term inside the parentheses because it has two i's and two j's. It means that you have to do summation. So you will start with 1 1 from I and 1 1 from j, and you will write it. And the third invariant is defined by this definition: 1 over 3 factorial times this term inside the parentheses, which is actually nothing by the determinant of B matrix. And the determinant is defined by epsilon ijk, b1i, b2j, b3k. So this is a fancy formula, but you know the determinant of a 3 by 3 matrix, and you can actually obtain it by different ways, like the uh, what we call it as a rule of Saros. You could calculate the determinant of this, and the formula is given here to you. Uh, the stress tensor invariants have physical meaning. So when you have a stress, the stress means sigma ij. This stress tensor, the first invariant of the stress tensor is the trace, as we said, and uh, as an exercise, I want you to find the second and third invariants of this stress tensor and try to explain these two invariants with a physical meaning. Okay, the first one is the trace of this stress tensor. The second one and third one, you will go and first of all, you will find them, their formula with these two definitions in here, and then try to relate it to some physical thing, actual physical thing. So these, as we said, these invariants should be the same in every coordinate system. They are invariant. They are not changing in coordinate systems. Using these definitions, we can also define principal invariants corresponding to principal axes. So principal invariants, if you have a principal matrix like this, you know that these are eigenvalues, right? The principal invariants are defined like the first invariant, the second, and the third. The first is the summation of the diagonal, or the trace. The second and the third. And the third is the determinant of lambda, and for the diagonal matrix, it's just lambda 1, lambda 2, lambda 3. You see that it is again important to be able to calculate all these eigenvalues, lambda 1, lambda 2, and lambda 3. And I can have any matrix written in random XYZ coordinate system, but if I can calculate the eigenvalues, not only I can have the directions of the principal axis, but also I can construct the invariance of that matrix. And the good thing is that to calculate invariance, I do not need to calculate principal axis because they are not changed with respect to coordinate system. Okay? From linear algebra, eigenvalues cannot be random, and they should satisfy what we call as characteristic equation. So the next thing that we have to study is this characteristic equation.